Hi, I'm Nicholas Asher. I'm going to tell you about fair and adequate explanations. Model explanations, those using logic, for example, offer us rigor, but they can be epistemically inaccessible. The explanations provided are simply too long or too complicated for humans to understand. And understanding is crucial. Explanations are something an explainer does for an explainee. They're answers to a why question posed by the explainee. Here's an example. E asks, why was I turned down for a loan? And why does she do that? That's because her beliefs don't lead her to expect this refusal. To answer her why question, we have to help her revise her beliefs. And how to revise her beliefs, that's the conundrum. An explanation, an adequate explanation should resolve this conundrum. Okay. So we're going to look at a particular type of explanation, counterfactual explanations. Here's an example that the bank might come back to E with. Your income is 50,000 euros per year. Had it been 100,000 euros per year, you would have gotten the loan. Now that counterfactual, conditional, gives a sufficient reason for E's getting the loan, given all other factors of E's situation didn't equal or being as equal as possible, ceteris paribus, given the assumption of a different salary for E. Now, counterfactual explanations are intuitive. They're typically more compact than non-counterfactual explanations because they leave the ceteris paribus clauses unsaid, and they also have close ties to causality. Now, in this talk, I'm going to give you a quick rundown of counterfactual semantics for machine learning algorithms for which we want explanation. I'm going to talk about how counterfactual explanations are both partial, but how we can move to less partial explanations. And then I'm going to talk about pragmatic constraints on explanations. And finally, finish up with a quick discussion of the complexity of finding fair and adequate explanations using a kind of game we developed in this paper. Okay, the counterfactual semantics for, in general, are a species of modal semantics. This goes back to Lewis's work in 1973. The one addition to a standard modal frame is a similarity relation. And the semantics for a counterfactual, noted with this box arrow symbol here, is such that the counterfactual psi arrow phi is true at a world W, just in case all the most similar worlds to W, where the antecedent psi is true, the consequent is also true. Now, the similarity relation has several motivations. One is epistemic. It comes from belief revision. In some sense, belief revisions to beliefs that are rationally justified should be minimal. And there are also metaphysical considerations that come from causation, where a causal statement typically assumes ceteris paribus conditions, boundary conditions that are left unsaid. Nevertheless, the similarity relation is unclear in Lewis's work and in other work also. We're going to interpret it as a distance relation over the set of inputs to our machine learning function f hat. In saying that the similarity relation is a distance metric, we'll be following Timothy Williamson's work of 1988. Okay, now, given that this notion of the counterfactual semantics, we can see a natural link to a different kind of formalization. Basically, what a counterfactual does, it asks us to move from one point of evaluation to a point where certain other conditions hold. So we can think of this as a kind of transformation on the space of inputs. Okay, some of these transformations keep certain dimensions of the inputs fixed. Okay, and so we could call one of these transformations appropriate if the value of the algorithm at the transformation applied to a point is a different prediction from the one that holds at the point itself, at the original point x itself. And it's minimal and appropriate if the point to which the delta I maps x is one that's the closest distance from X, where the prediction of F hat is different. Okay, now these transformations can be linked and have been linked, or really linked to adversarial perturbations, and can be found relatively efficiently. Now let's try and adapt our counterfactual models to our machine learning world. Well, we're going to have a language for our machine learning algorithm for predicates for the features of the input and predicates for the predictions. The similarity relation will be defined by a norm on the space, and the interpretation function will have the natural property that if the feature formula where a feature has a certain value in A is true at a world W, that will be the case just in case W has the feature A. And similarly for the prediction formula. Notice that the main thing we've done is we've identified our possible worlds in the original counterfactual model with now the inputs to our learning algorithm. Now, given this way of thinking of a counterfactual model for our learning algorithm, there's a natural correspondence between counterfactuals and minimally appropriate transformations. And we can also link these minimally transformations, the minimally appropriate transformations, to deductive explanations in a worst linear number of calls to an NP-array. Now we have our notion of counterfactual explanations in place. We have the semantics in place. We've said that counterfactual explanations are more compact. In fact, they're partial, and they're partial in three ways. First of all, they're deductively incomplete. In contrast with deductive explanations, they don't specify all the conditions necessary for a full proof of the prediction. Why? Because of the ceteris paribus clauses that are left unsaid. Counterfactual explanations are also globally incomplete. They don't specify all the sufficient conditions that lead to the prediction. And finally, they're locally incomplete in the sense that a prediction can have several explanations at a given point. This is what happens when this happens, we say that the prediction is overdetermined. Okay, so right, a local one counterfactual may give only one of those explanations in an overdetermined case. We can move from these partial explanations given by a single counterfactual to more global explanations, of course. First of all, by looking at the set of all those counterfactuals that are true at a given point, where pi is in the consequent of the counterfactual. That gives the complete explanation for why pi would have occurred at X. And this set of counterfactuals defines a boundary in the space around X, and we call that space around X a certain kind of neighborhood. Now, because we're interested often in, most often in explanations for what happened at a particular data point, X hat, we're going to limit this boundary to a pragmatically defined distance. What's interesting about this boundary and the space that it defines, this neighborhood, is that the structure of the set of counterfactuals, in particular the flip degree, tells us about the topology of that space. And the flip degree has to do with how the counterfactual, the consequent changes truth value as the antecedents of the counterfactual become more specific. To give you a picture of what this might look like, here you can see this yellow area around X hat. This is the neighborhood, and the different colored splotches here are the action of our function on points where the predictions differ from those around X. So the boundary of X hat is this line, but it also contains this line and this line. You see the space is not at all it's not at all homogeneous, really. It's not smooth. And this is typical of counterfactual explanation. Okay. Now let's move quickly to the pragmatic constraints. Our explanatory conundrum comes from a mismatch between understanding of what F hat was supposed to model and F hat's actual predictions. And this can come about for several reasons, but we're only going to look at three here. Our explannee's model of F hat can be incomplete. She might not know of certain features that are crucial for the prediction. She might be mistaken about the values that that certain features she does know about. And finally, there's something important. F hat might be unfairly biased. This is a particular case of either two conditions above, but we think it's important to separate it out because a set of counterfactuals that provides a fair and adequate explanation of the behavior of F hat for E at a point X should should make clear all the biases that may be unfair to E, as well as these epistemic, as well as remedy these epistemic problems of incompleteness or mistaken values. Okay, well, how complicated is this search for a fair and adequate explanation? To investigate this question, we developed something called explanation games, where the explainee E plays with an explainer A over elements in the space of the algorithm, and in an attempt to explain the behavior of that algorithm. And the game ends when E solves her conundrum. Now, E, we assume, will always has a winning strategy to solve her conundrum. The question is, how long does it take her to find that that winning point? Well, it depends on what kind of moves E has available to her. She might request a particular transformation, right? A particular set of features that shift. What happens then? Or she might just request a transformation she's not seen before. Or she might challenge her opponent by proposing a particular transformation to which we can stipulate that A has to respond with a correction or completion of the values of the xi's in that delta I. Okay, when E and A have aligned preferences, an explanation game is a signaling game with equilibrium where E solves her conundrum. And that equilibrium can be solved in linear time or maybe sublinear time. But players may not have aligned preferences. The bank may not want to explain its decisions, at least not explain them in full to all of its customers. Well, if E can play a particular request or just a new request, the computation of E's winning strategy in G is polynomial local search complete. On the other hand, if she can only play n requests, which is what we call a restriction game, then the worst case complexity for finding her strategy is exponential. Finally, if she can play challenges, then she has a winning strategy that's linear time. Okay, our conclusions are that explanations are pragmatic acts, and that's something important that the literature is kind of largely overlooked, at least recently. And explanation games are a very useful tool to help us understand better this pragmatic aspect. We think also that explanation games hold exciting prospects for investigating interactive explanations, actually, where we have a dialogue with the learning system. This falls into interactive machine learning paradigms, and we think that's very interesting. What we've shown is that counterfactual explanations provide partial but adequate and fair explanations, or can do so. We've provided a valid semantics underlying these explanations. Nevertheless, moving from that semantics to a proof from a minimal set of sufficient premises is still computationally difficult, and we'll have to use various kinds of heuristics to get that practically solvable. Thank you.